strange thing about this model, even when I published it, and even though it's been downloaded a lot, I've never had a criticism of it, a formal criticism from an astrophysics person. I would love to see people coming out and criticizing it in the literature, saying, look, this stuff by Johnson is totally crazy, and why would we believe him anyway? And but I've had none, and I encourage people to do that.
Today's episode is perhaps the last recorded conversation with MIT physicist Keith Johnson. Keith was an unconventional thinker whose work spanned quantum chemistry, materials science, astrobiology, and even science fiction filmmaking. He was part of the legitimate effort to verify cold fusion claims, and eventually filmed a full-feature sci-fi thriller set at MIT about a female MIT professor who discovers a sinister cold fusion cover-up.
So it's really amazing that you have so many talents, and I would like to ask you, like, how did your career path lead you to explore like both scientific research and screenwriting?
Thanks for the question. It's kind of a long story, but since I guess you have some time, I'll try to trace it out as succinctly as I can. First of all, I was born at an early age, and at the age of 11, my aunt bought me a chemistry set back in Pennsylvania, which is my origin. And that started my interest really in lab chemistry. And through high school, my plan was to be a chemist, to go to university and be a chemist. So I went to Princeton and on a scholarship. And as soon as I got there into the basic chemistry class, I was pretty much bored by it because I had done a lot of the experiments in my home lab, which by then had occupied the cellar of my parents' home. And I decided to change my course. Princeton is a very flexible place. So I stopped the chemistry studies and went into physics. Took freshman physics, had a great teacher, John Wheeler, who, I don't know if you heard the name, but he was my freshman physics instructor, and had courses with some of the top people at MIT. Robert Dickey, who was a physics professor and did some of the earliest experiments on the background rate, trying to detect the background radiation of the cosmos, and even Robert Oppenheimer. I had a seminar with Robert Oppenheimer. So anyway, following Princeton, I have
do you remember any interesting, like,
also minoring in astronomy and music composition there. So physics was my major, astronomy was a minor, and music composition was sort of a side interest. So after that, I went to graduate school. Started out at the University of Pennsylvania in physics, and connected with a gentleman who is a theoretical physicist. But he ended up moving to Temple University. It really just started at University of Pennsylvania, and Temple University was building up its physics department, so he went over there, and I followed him. And just as now, in those days, you did what you could get research funding for. And fortunately, he and I got research funding from what was then called the Atomic Energy Commission, now known as Department of Energy. And the problem there was to study the electronic structure and optical properties of metal alloys. It's far removed now from dark matter and dark energy. And we developed some computer programs to do those calculations. And that was that. It was an interesting subject, and we published it. And then I had to consider what to do after. Try to get a job or go on to graduate school, further graduate school. And I thought of studying medicine, but I got a call actually a few months after I completed the thesis, to join Professor John Slater, who was then just about to retire as the head of the physics department at MIT. And he is was a pioneer in the quantum theory. He had started at Harvard, and he went off to a postdoc with Niels Bohr, and came back, and MIT hired him to run the physics department and build it up. At that time, when he joined the physics department at MIT, it wasn't all that big as it is now. And so anyway, I decided to do, at his invitation, to do a postdoctoral period of, with him. And he was spending half his time at the University of Florida and half his time at MIT. And he would come back in the summers and so on. So I did that down there, and that's where I developed, with his cooperation, a new method of calculating the electronic structures of molecules and materials. And it was called the scattered wave method because, unlike other methods in quantum chemistry, it started out by looking at the way electrons behave in atoms and molecules and solids as a kind of multiple scattering problem. And by programming this, we programmed it in Fortran at that time, you could deal with much more complicated molecules than you could by other methods of quantum chemistry. So here I was, having studied physics at Princeton, continuing with sort of a physics problem in graduate school, now getting back into chemistry, quantum chemistry. And let me just mention one big difference between the way physicists look at solids, materials, for example, at MIT, the material science department, and so on, and the way chemists work. Physicists tend to work in momentum space. Sometimes that's called K-space in solid-state physics language. This is reciprocal to the space in which we live. Chemists live in real space. And of course, this all connects with the Heisenberg uncertainty principle because, I'm sure you know this, Heisenberg introduced essentially quantum theory with the famous Heisenberg uncertainty principle, where he said you can't locate a microscopic, a nanoscopic, or subatomic particle simultaneously in real space and momentum space. And that's expressed with a very simple mathematical formula. So whereas chemists work in real space and physicists tend to work in momentum space, and that's true.
So the physicists are Fourier transformed?
Pardon?
Sounds like physicists are Fourier transformed.
Yes, exactly. Exactly what they are. And that's true not just of solid-state physics, materials science physics, but it's also true of all the areas of physics, including particle physics, which I'll get to in a minute. So where was I? So I developed this with Professor Slater. In the postdoc, I developed this scattered wave method, and we started to apply it immediately to molecules that you were not able to describe by solving Schrodinger's equation for that molecule, because these other methods were much more complicated, involved just many more terms that you had to evaluate, called multi-center integrals and so on. So one of the first areas we started to look at were biological molecules, where there was very little first principles quantum chemistry being applied to that. And then what happened was there was an opening at MIT in the physics division. At that time, the material science department. And Misha, I think you're in the material science department, right?
Material science engineering, yes.
Oh, okay. So at that time, the department wasn't even called Material Science and Engineering. It was called the Department of Metallurgy, believe it or not. And but the department was divided up into different areas. One of which was solid state physics. Okay. And it turned out the physics department at MIT wasn't doing much solid state physics at that time. So the solid state physics was done in the material science department. There were other areas like ceramics, and there was true metallurgy in in the Department of Metallurgy, of course. And there was a separate division on polymer science. And so that's the way the materials, what you now call the material science department, was divided up. So with Slater's recommendation, I became the resident solid state physicist in the material science department and continued to develop this scattered wave method, quantum chemistry method, to attack molecules. So the other interesting thing about that method is you could also deal with solids. So you could study metals, you could study ceramics, you could study polymers, but you could also study biological molecules um, using the same method. But you ended up working in real space, not momentum space, not K space. And when you work in K space to study the electronic structure of a material, it's called band structure. And I'm sure you guys are familiar, you've seen publications on it. At that time, band structure and Fermi surfaces and experimental techniques that elucidated the K-space behavior of solids was very popular. So in any case, that's what I did for many years at MIT. And I worked not just in the material science department as this resident quantum chemist band structure guy. I also interacted with a lot of people in other departments. So one of the departments that we applied this method, the scattered wave method, to was the Earth and Planetary Sciences department. And for example, one of the first things we did was study the optical properties of the moon. And it's sort of interesting because a lot of that work is now coming back into popularity because of new moon missions and so on, and potential moon missions. So the thing is that by working with other departments, I also worked with the chemistry department, with professors in the chemistry department who were interested in biological molecules. One of them was Professor Cotton, who unfortunately ended up not staying. Maybe it was due to working with me, I don't know. But the thing is, he was maybe the top inorganic chemist in the world at that time, and had co-authored a textbook on inorganic chemistry. And he and his students, who I was co-advising, would apply it to stuff they were interested in. And let's see, I also interacted with the electrical engineering department. There was a guy there named Adler, David Adler, who was the resident physicist, theoretical physicist, or solid state physicist in the electrical engineering department. I mean, one of the great things about MIT is the interaction and fluidity between different departments. And maybe you guys have experienced this. And so the thing is that David Adler, he was applying the scatter wave method to calculate the electronic structure of solar materials. And he was one of the early pioneers in trying to understand how and why solar cells worked. So anyway, the experience at MIT was great because of not just my own focus, but the ability to, a chance to interact with other people. So out of this came a lot of publications. And then what happened was in the 90s, a couple of things happened. One was cold fusion, and I'm sure you also knew a little bit about that history. Um, these two guys from Utah, Pons and Fleischmann, came up with this on television, basically, the claim that you could create nuclear fusion on a tabletop, on your kitchen table. And of course, that spoke interest on the part of a lot of physicists, especially nuclear physicists, who didn't believe that anything like that could ever occur, to get interested and start doing their own experiments, and not the least of which was MIT. Uh, and why should they be interested? Well, there's a fusion lab, a nuclear fusion lab at MIT, that's been there since, I guess, the late 50s, when nuclear fusion, the first nuclear fusion reactors were developed. For example, there was the tokamak back at Princeton, and then they developed their own fusion reactor at MIT, which is still there, and has been funded for years. So that development, cold fusion, sparked my interest in it from a theoretical point of view, because I didn't believe myself that fusion was on a tabletop was possible from what I knew about it. And then what else happened? At the same time, I was developing an interest in screenwriting. I had been, in 91, I had been on a second trip to Russia as a consultant, technical consultant, for Dean LeBaron, who ran an investment company in Boston. And we were friends, and we flew over there. Well, my wife and I flew over there the first time. Everything was fine. The second time I went over there, it happened to coincide with the infamous Russian coup, the coup. And when things changed overnight, literally. And so I...
So you were there in 1991?
1991.
Okay, so that was exactly during when the coup against Gorbachev, or that was like
Yes,
right
exactly.
collapsed.
I remember.
Was it the first one or the second one? Transition.
The second one.
Okay.
The second one. And I remember going to a gathering at the Parliament building one evening, and there were tanks. Well, first of all, my first experience there was seeing the tanks roll into Moscow, and we were actually staying. I was actually staying at a dacha that was owned, of course, by the previous, the government at that time. And I remember you had to be careful of what you said in the bedroom, for example. Don't face up to because up in the ceiling there's a microphone. But anyway, so within 3 or 4 days, all this happened, and the tanks came rolling into Moscow, and I was there, accompanied by a secretary of the man I was of the branch of the man I was working with over there. And I remember, there were some cars piled up. Unfortunately, the secretary I was working with had a little car, small Russian car, and we were able to negotiate a trip from the center of all this activity back to the dacha where we were staying. And we had to make a decision, because I wasn't the only one on this trip. There were gentlemen from different companies who were planning to invest in Russia, in technologies. And that's why I was there, to kind of assess these different technologies from a theoretical point of view. And one evening when all of this was happening, we had to make a decision whether we were going to try to fly back to the United States or to go to to go on to Kiev, which of course is now a center of activity, to interact with some materials science people down there, and also visit the proton rocket plant. I'm trying to remember exactly how those two decisions made. Anyway, we had to make a decision and whether to fly back. And we decided to stay. And then, just like the ending of a Hollywood movie, things settled down. One of the funniest things that had happened is the tanks that were gathered around the Parliament building one evening. They expected some kind of an incident to occur, and it turned out something was happening, and it turned out just a delivery of pizza to the Parliament building. Anyway, the thing is that things worked out for the best at that time, and we ended up staying. We ended up having meetings with not just in Russia, but in Kiev. And I visited a lot of companies, not the least of which was a company specializing in audio equipment. I'm an audiophile, and somehow the woman who was watching was heading up the a branch of a company. I think it was called Ocam Prebar, which was a company specializing in undersea water detection equipment, which probably was used to detect submarines and things like that. But also, they were moving into the area of fisheries. But anyway, there was a small division of this company that was specializing in, of all things, audio equipment, including phonoplayers and amplifiers and loudspeakers. And somehow this woman knew about I don't know how she knew about this, but she knew about my interest in audio. And when we left, she had arranged to have all of this beautiful Russian audio equipment, which at that time was only affordable by very few people, loaded on our airplane. And we brought it back to the United States. And there's another story connected with all of that. But anyway, the total experience in Russia, both the first experience where my wife Francisca joined me, and the second experience was like being in a Hollywood movie itself. At the same time, I was developing an interest in screenwriting. And the way that happened was on our first trip, we had gone to the ballet. And in what's now called Leningrad again. And I was very impressed, of course. I'm also, being an audiophile, I'm also a music file. And so what happened was I started thinking about, why don't we dream up a story about Russia and the United States, a thriller, so to speak, about a ballerina and some bad guys who are trying to sell a substance called red mercury. I don't know if you've ever heard about that. But red mercury was a substance that Russia was trying to convince the world existed. It was a substance from which you could make nuclear bombs the size of a teacup. Okay? So I fashioned a script about a ballerina, this happening, whose father, by the way, was a former member of the military, and the whole dance scene over there. And then also some bad guys from the United States who were trying to buy this stuff and sell it to bad guys in other countries like North Korea. And so I wrote this script, and immediately after we came back, I sent it to somebody I knew in Hollywood who expressed an interest in it. And so after a couple of trips to Hollywood, we tried to get interest to sell this script to make a joint production with Len Film Studios in Leningrad and the United States. And um, so what happened during that, actually, some of these people from Len Film Studios came over and to Hollywood to try to get this movie made. But things didn't work out, as many things don't work out in Hollywood, regarding the funding and how it would be shot and so on. I decided to turn my interest to another area, which was happening at MIT, namely the cold fusion thing going on. And I said, well, why don't I write a story about a young professor at MIT, in this case, a young woman, female professor, who's not a professor of cold fusion or anything close to it, but she's a theorist, like I am, interested in dark matter. Okay? Now, at that time, the mystery of dark matter, this was even before dark energy was discovered. The mystery of dark matter was present very much, and there were many other physicists in the world trying to find out and theorize about dark matter. What is it? What is it really? So I fashioned a story about a young female professor who tries to get a job at MIT in astronomy, but doesn't actually, there's no opening. So she ends up working with the plasma fusion lab at MIT, which really exists. And she's hired by this rather pompous professor and head, a fictional guy, of course. This is all fiction.
I watched this movie in preparation, and I'm curious whether the professor is based on like someone you knew.
Good question. No, not really. He's a total fiction. He's pompous. He's funny. He's really the comedy relief of the movie, because it's a pretty serious movie. And so he became comic. So there's nobody really I would mention that I patterned him after. No, not at all. And however, the Fusion Lab stuff, which is, as I say, Fusion Lab still exists, was in the background. And as soon as she gets there and starts to work for him, he's pressuring her to try to apply her theory of plasma physics in stars, stellar path, to solving their plasma physics problem. Now, as you know, hot fusion, is still very much in the news, and maybe more than ever, because there are all of these startup companies, some of them, at least one from MIT, that are competing with each other to make fusion practical. But certainly at that time when we made the movie, there were none of these companies, and most of what was going on in fusion was happening at universities and at places like MIT. And so as soon as she's hired by this guy, he's kind of a sexist guy. He threatens her. He reminds her of what getting tenure at a place like MIT. And by the way, I never called the place she's working MIT. I called it the Institute. There was plenty of other realistic scenes in it, but I never wanted to use the term MIT. And I did have
Was
some
it
trouble
easy to get
filming it.
MIT to agree to film because a lot of it was filmed at
That's where
MIT?
that's the fun part. MIT had a policy. Well, years before that, there was a thriller filmed at MIT where they actually shot some footage on the Great Court and did some damage And after that, MIT, just like Harvard does, you're not allowed to make films. Maybe a documentary, but no, narrative film on the MIT campus. And I had a
What
friend.
about the following? I think it most recent movies, 21 and the Social Network. Sorry, that was about Mark Zuckerberg. I think it was 2000 something, and then
That
21
probably
is
wasn't
where
filmed. That probably wasn't filmed
MIT
on the campus.
MIT students. I don't know. It looks like pretty much. Maybe they mocked it, but it looked
Well,
like
I don't
MIT.
know if they
So
actually filmed it there.
yeah.
Uh, the At this time we were filming this movie, which we called Breaking Symmetry. Uh, Goodwill Hunting was being filmed, which is a very famous film, much more famous than ours. Was being filmed in and around Cambridge, and it started the career of Matt Damon, as you know, and who is a big star in Hollywood now. And the thing is that he was supposed to be a student. I'm sorry, a not a, he was working for facilities in this in that story, but he was supposed to be at MIT. And there's some scenes where he's supposed to be in the halls of MIT and writing equations on a blackboard and so on and so on. I don't know if you've ever seen the movie, but it won several Academy Awards and so on. But anyway, at the time we were making the movie, you were not supposed to be filming on campus. However, I did send a letter to the uh, officials at MIT that I wanted to make a movie there, and would they make an exception? They never responded to it. So in any case, I decided to shoot there anyway, and just exteriors, and at the entrance to MIT, and did some guerrilla shooting myself in the halls of MIT, and that was that. We started to make this movie. Part of the story of this young woman who's trying to become a professor at MIT and hopefully a tenured professor eventually is that she discovers that she's replacing another woman who had been working in the plasma. I'm sorry, who had been working on cold fusion. Okay, and this woman was found dead in her apartment with her um, faculty partner and so on. And so this was kind of a secret that the character didn't know about. So she got very interested in cold fusion. Even though she was a dark matter theorist, she became interested. Is cold fusion for real or not? Because her supervisor, this other professor who I call Professor Klinger, fictional character, was definitely opposed to cold fusion. And in fact, at that time, MIT had tried to replicate the Pons and Fleischmann experiments and were not successful in showing any excess energy as fusion should show. So in the process, we developed a story which kind of connected the whole cold fusion issue and what's happening in a cold fusion cell, which has water in it, okay? And this character, Carolyn, the young professor, interest in dark matter. Okay, so so anyway, the thing is that her theory, which at that time was pure fiction, as far as I was concerned, was the idea that water clusters of water molecule in the cosmos, had something to do with dark matter, and pure fictional invention at that time. And and then what happened was coincident. Well, first of all, I should point out about the making of this movie. Originally, it was represented in Hollywood, and I had an agent at CAA, which is one of the premier intellectual property literary agencies in Hollywood, and they were very interested in Breaking Symmetry as a Hollywood movie. And unfortunately, what happened, as often happens in that place, is new ideas get circulating around Hollywood. And what was the idea they were circulating? The idea of a female cold fusion scientist. Okay? And within a year of my film, my original script, which was much more complicated, being circulated around Hollywood, and ending up, I think it was Paramount Pictures, 3 other movies ended up being made about a female cold fusion scientist. Now, what's the probability of that? So the thing is that one of them was called IQ. I don't know. You can find these. You can stream these movies made in the 90s. One of which was IQ with the actress Meg Ryan. The other one was um, Chain Reaction with Keanu Reeves. And the third one was The Saint, which was actually filmed in Russia. That's what's really interesting, is The Saint. If you watch the movie The Saint, you'll see scenes filmed in Russia. And it's all about female scientists interested in cold fusion. So I got very annoyed by this because I'm here. I'm not out in Hollywood, and my agent said, "Look, these things happen in Hollywood," and at the same time, I was communicating with Arthur C. Clarke, the famous science fiction writer, who had made, 2001 with Stanley Kubrick and so on, and we would communicate by fax. I was communicating with him because he had so much experience in trying to get his stories published, made into movies. And he told me, he said, "Look," he said, "these things happen in Hollywood. You should just go and make the movie yourself." And so that's what we ended up doing. It took us a couple of years to get it together, but we made Breaking Symmetry at MIT. I remember one scene we were shooting outside one of the entrances to MIT, and one of the MIT police, stopped, and I knew him. He was a very friendly guy, and he says, "Oh, are you? Do you have permission to do this, Keith?" And I said, "No, I tried to get permission," and so on. So somehow he communicated that I told him the scene would not take very long. It was an outdoor scene and so on. So we ended up shooting that movie, a much smaller movie with local actors, all total local actors, and we financed it ourselves. And it was just an experiment on our part. But anyway, you can now
So
see it
actually,
on.
I'm curious. Like at that time when you film the movies, I mean, these days when I see like some recording on the streets, there's like a huge, usually like the whole block is, occupied, and then there's like huge trucks, a lot of light, a big crew working on that. How was it at that time when you recorded that? Like how if you could describe what was the stage like?
Well, actually, that scene where the interaction with the MIT policeman happened, we were filming on right by the river across from MIT. And we had a scene with a taxi pulling up, and we had a camera car. We arranged all that properly. So, except for some indoor shooting at MIT, which I did myself with my own camera, everything was done according to Hoyle. It was all done according to union regulations. We had very good people on our crew. We had a pretty big crew, and we arranged everything properly. And one of the problems we did have was we were supposed to get rid of all the parking on along the river, and a lot of people who are used to parking at MIT didn't want to do that. So I think some of them got their cars towed away. But we did everything properly according to oil. Every place we filmed, we arranged it ahead of time, and we paid all of our actors and all of our crew. So it was not, and it was all shot on film. This was just at the point at which digital filmmaking was becoming possible, but it wasn't good enough. So we filmed everything. We did everything on film, and we shot it in about we shot it 5 days a week, because the other 2 days, and this takes us to another part of the saga. The other 2 days of the week, I was helping start a company, a spin-off company from MIT, which was called Quantum Energy Technology. And the head of that company, the management of that company, was by a man who had been in the technology transfer department of MIT, John. So the thing is that John Preston was his name. In any case, I was doing that the other 2 days of the week. So we were filming, I think, on Saturday, Sunday through Wednesday or something like that, and then I would work 2 days at this new spin-off company. And what was quantum technology doing? Well, at that time, sources of pollution, trying to clean up pollution in vehicles, was a very important area. So we ended up trying to work on a way of treating diesel fuel in vehicles, both public and private, to clean up the air from the combustion. And I found some evidence in the literature that if you mixed water and oil together with surfactants, these are chemicals that allow water and oil to be happier together, you would produce much less carbon dioxide, carbon monoxide, nitrogen oxides, and so on. So we tried to improve on that and develop a treatment for combustion in diesel engines. And we worked on it with this startup company called Quantum Energy Technology. And my work was mainly to guide them regarding how you would formulate these additives that you would introduce into the diesel engine. And we did tests on it on buses, and not just in Boston area, but also in Costa Rica. And that happened for a couple of years. Let's see, 2 or 3 years. And the goal was to commercialize this. And most of my work, again, was purely theoretical. And as I was doing this work, I discovered more and more evidence that these clusters of water molecules that were introduced as a plot point in Breaking Symmetry, the movie, the fictional idea that somehow this had cosmic significance. What do they look like? Well, they look like this. They're dodecahedral. This is a pentagonal dodecahedron, and it's got 20 water molecules at each of the vertices here, okay? And hydrogens are sticking out. And it turns out these water clusters are nanoclusters. That's what they are. They're nanoscopic, 10 angstroms. turned out to be, I discovered from early work of Linus Pauling, of all people, whose name you probably know in chemistry, Nobel Prize winner in chemistry. He had pointed out way back in the 50s that the structure of liquid water, if you try to understand liquid water, and that has been a challenge, the properties of liquid water are one of the most challenging things to try to explain for years. And he came up with the idea, Linus Pauling, that that the water molecules in liquid water actually form these dodecahedra under certain circumstances. So of course, it's very dynamic, very dynamical. And so you have to think of, in liquid water, that the water molecules can arrange themselves like this, but very dynamically. They're not just rotating, but they're also fluctuating, like a soccer ball in a sense. Okay, and so it turns out these nanoemulsions which we were trying to develop, the goal at Quantum Energy Technology, this spin-off company, which we were just starting while we were making the movie. The structure of these things depended very much on this kind of structure in the nanoemulsions. We wanted to create nanoemulsions that actually involved the water part forming these entities. Now, why would you want to do that from a microscopic point of view or a nanoscopic point of view? Is because they have very different properties. In other words, if you carve out of liquid water these clusters and are able to stabilize them, they have very different properties from ordinary liquid water. For example, they have a spectrum, a vibrational spectrum. In other words, if you analyze the vibrations of this thing, it's not just the oxygen. At each of these earths, there's an oxygen atom. It's not just the oxygen vibrations, but the whole buckyball. This is like a carbon buckyball, which I'm sure you've also heard of.
Is there any way to image those water clusters, like with any kind of microscopy? Is it possible to image them? I don't know, maybe like STM or something like that, like where you could see
There
the
are people
structure.
who claim that they have imaged them, yes. But because they're so dynamical, in other words, they vibrate on their own, and they vibrate, the types of vibrations I'm talking about where the whole cluster vibrates. There are two types where the whole thing sort of swells. In other words, bounces like a soccer ball. But then there's also very complicated twisting motions that go on, and so it's very difficult to image them. To answer your question, to image them.
But do you see them? Do you see them in maybe like while doing some sort of like a spectrometry? So that like the spectral vibrations.
You can do Raman spectroscopy, okay? Raman spectroscopy, and you can do X-ray spectroscopy. And there are claims, especially if you go to low temperatures where you freeze these things, you can get indirect imagery of the fact that these dodecahedral water clusters are stable at low temperatures, okay? But to actually see them, to actually put water under a conventional microscope or even an electron microscope, it's very hard to see them individually. But we know they exist, and you can measure them spectroscopically with mass spectroscopy. In other words, you can take a beam of water and you can do what is called mass spectroscopy, and then you can look at the mass of these clusters and then infer what their shape, what the number of atoms are, and so on and so on. So while there's been a lot of advancement in trying to image even atoms, as you know, on stable solids, especially semiconductors, it's very difficult to image these things directly, except at very low temperatures. Okay? Now, as far as making nanoemulsions, which was our goal, in which we created these things, we had to infer indirectly that they exist. Anyway, we never ended up commercializing these nanoemulsions to clean up the diesel combustion. But we did have some side areas where the same physics or chemistry was potentially useful, and that was in cosmetics, of all things. In other words, the microemulsions and nanoemulsions that people use to treat their skin. And we got some interest from DuPont and so on in buying into it. But eventually, it just never was commercialized because other technologies came along to clean up diesel. And of course, this was also the beginning of the onset of other means of propulsion. But anyway, out of all of this was because we were filming this fictional movie, science fictional movie, and developing this chemistry, that I started to think, well, maybe these water clusters are actually have interest, especially if they're stable at low temperatures. What about in space? Water, I mean, remember, our bodies are 70% water, our brains are 75% water, and the Earth is 70% water. And there was plenty of evidence for water molecules existing in space. They can be identified spectroscopically. All you have to look, since you can work out the electronic structure of these buckyballs. In other words, using the scattered wave method, which I had developed earlier, it was easy to calculate the electronic structure and properties of this thing. And the point is, you can identify them spectroscopically anywhere if you have the right equipment. And just like you can identify the presence of water molecules. However, distinguishing this arrangement from other arrangements, for example, icosahedral arrangements, is a challenge. In any case, it seemed to me that maybe the fictional idea, that water clusters of this type might have some relevance in the cosmos, as it has relevance in other areas of chemistry and maybe also in biology. Why not pursue this? And because the fictional character I had developed for the Breaking Symmetry movie was a dark matter theorist, this young woman, why don't I start actually thinking about this? And so I started studying the state of the art in
I
what
guess
is now called
one
dark
question, but before you go into that, I'm just curious. One question: how were you? Because the movie was partially about cold fusion. How involved were you in cold fusion? Like, it'd be interesting to hear your account of kind of what happened there, starting with '89, and then what's your take on it in general? It'd be curious to hear
Well,
because
my
you
take
were
will be
around
interesting.
at the time that it was happening.
Yeah. Okay. Good question. First of all, I didn't believe that cold fusion was real, just as MIT and other institutions investigating were not getting good results at the
Is
level they
there a
were claiming.
physical limit that like guarantees that it's not possible, or it's more like something that it couldn't be shown?
Basically, the answer is, and this is what I ended up publishing in separate papers. I believe the cold fusion, there was a level at which cold fusion was actually occurring in particular materials. And the material of choice was palladium. In other words, when you dissolve hydrogen into palladium, you start to approach something called palladium hydride. And experiments that had been done by other people after Pons and Fleischmann showed that something was going on in palladium hydride. However, it was not terribly stable. For example, it seemed to work better to get some excess energy at a very low level out of palladium that had cracks in it, that had defects in it. And I was interested in that too, because at that time there was a lot of interest in material science, in defects in materials, especially metals and so on. There were other people in the department working on that area. So the thing is that in the final analysis, my own theoretical work essentially argued that cold fusion is real at a very low level. In other words, you can get some heat produced, okay? You can measure the heat produced in the laboratory. And if you calculate how much heat versus the energy you put in, there was a little bit of it coming out. But you would never end up powering a house, okay? Substituting or competing with solar energy or conventional electrical energy using a cold fusion cell in your house, which is what Pons and Fleischmann were trying to sell, sadly. And there's an interesting side story about this, because about Pons and Fleischmann, because they left the country, as you know, because there was no, except for a few places, there were no laboratories that were getting results consistent with what they were claiming. And Pons moved to France, and Fleischmann went back to England. And it turned out we were at the Cannes Film Festival, again in the 90s, and trying to get some financing for filmmaking. And I realized that Pons, the younger guy, Pons and Fleischmann, was living not too far from Cannes, France. And I found out more. My wife and I ended up staying at a hotel in a small town outside of Cannes, where the film festival was going on. And the hotel owner said, "Oh," I asked him, "Do you ever heard of this fellow Pons?" "Oh, yes, famous cold fusion guy from the United States. Yeah, he has a drink with Fleischmann at this bar across the street every afternoon." So there we went. It turned out we went over there, and there was Pons having a drink at this bar in this small village where he was living. Well, it turned out not only was he living in that area, but the Toyota company, the owner of the Toyota, spelled Tyoyoda, famous automobile company, had established for Pons and Fleischmann a big laboratory near this town. It was sort of in an area which you might be called the Silicon Valley of France, all sorts of technologies. And so when we went to the bar, and I recognized Pons, and I tapped on his shoulder and I said, "Professor Pons, I sure." And then he turned around, and he didn't know me, of course. And then I introduced myself and I said, "Look, we're going to make a movie in which there's cold fusion is part of the subtopic of the film. It's a science fiction movie. I'd love you to read the script, and I'd love to see your laboratory." So he took my wife. The next day, my wife and I went and visited his laboratory, where he's huge laboratory, beautifully outfitted. And
Does it still exist? And how many people were in the lab?
when we went there, there weren't a lot of people. And that was one of the surprising things. It was just beautifully outfitted and so on. And he told us, we're going to have cold fusion generators for the home in a year. Okay? And he's really a nice man, really. And I knew he believed in what he was saying. But I had my own reasons, and I risked giving the script to him. It never mentions their name, but it comes out with a very negative result for cold fusion in the script. But he liked it. He thought, oh, it's science fiction. Doesn't matter whether you believe in cold fusion or not. But what happened to this lab? I really don't know what happened. Other than that, they stopped. They ran out of money. Toyota didn't support them anymore. There were other labs in Japan, and I think there's still a lab in Japan somewhere that is doing work. And the U.S. government now, strangely enough, until the new administration, has been supporting research on cold fusion in certain places. Even the United States Navy Research Lab has had some work going on, and they no longer call it cold fusion. They call it low energy nuclear reactions, LENR. And so, in a sense, it's come back again with claims more or less focusing on what you need to do to palladium and other materials to get this reaction occurring at a higher level. But still, no one has, as far
Can
as
you
I
maybe
know.
explain what's the working principle? Like, how is it supposed to work if it works? So, like
Well, there are all
inside
sorts of
palladium, or
claims. And there's a professor at MIT named Peter Hagelstein, friend of mine. You can look him up. He's in the electrical engineering department. And he still publishes theories for how he thinks cold fusion works or should work. And he's got very complicated new reactions. My own work in this was much more chemical in nature. And it was the idea that if you look at the crystal structure of palladium, it's face-centered cubic. But what happens is when you start to fill it with hydrogen, which is the way the electrochemical cells work in a cold fusion cell, the hydrogens go into tetrahedral sites, and by the way, we're not talking about hydrogen alone. We're talking usually about deuterium, which is the heavier isotope of hydrogen, which is the thing that actually was believed to fuse. If you stuff enough hydrogen into palladium, then the hydrogens start to overlap in their wave functions. This is, in other words, the electronic structures start to interact. And that influences the vibrations of the whole system. So you get a kind of electron-phonon interaction going on. And under those circumstances, the hydrogens, which go into the tetrahedral sites, start to move around, vibrate, and that increases their nuclear fusion cross-section. And you can actually calculate how that increases the probability of actual getting fusion. And actually, we published a paper on this. I'd be happy to send you the paper on it with all the diagrams and so on and the visuals. But we also got a patent on it because we discovered that if you alloy palladium with other elements like nickel and so on, you can enhance this interaction somewhat. You're not going to get enough heat produced to even light a bulb. Okay. However, you will measure some heat, excess heat, and this is something we demonstrated actually in the movie Breaking Symmetry.
So how much heat can you how much can you get it, like maybe theoretical, experimentally?
How much heat?
Yeah, how much heat? What's like the value? Is there a way to estimate it?
Let's say you can put 25 watts in and get 27 or 28 watts out, maybe at the best. The main problem with cold fusion is the materials. Once you start loading palladium, what kind of palladium? Palladium, first of all, is not cheap. Secondly, is it high-grade palladium? Is it structurally free? Does it have cracks in it? So one of the problems with getting even a reaction of what we're talking about is consistency. And this was the problem from the beginning, is that people who tried to replicate Pons and Fleischmann's results failed in every case. Now, with this new area of low energy nuclear reactions, people are trying to solve this problem. So there are a few places that were getting funded. It started out, for example, at the Los Alamos lab, and then there was some work in California at one of the California universities, and then in the U.S. Navy. And I haven't really kept up with it to find out if they've gotten anything that's publishable. The problem is that the majority of the physics community doesn't believe in it, and from the level of commercialization that Pons and Fleischmann believed would come from this, I don't believe in that would ever happen. And they shut down the laboratory in France, and I don't know what's happened to Pons. I guess he's just retired. But it's an interesting subject, and I do think it's worthwhile continuing to look at mainly from a material science point of view. In other words, even though Peter Hagelstein in the electrical engineering department at MIT is still working on it from a theoretical point of view and has published some papers recently and claimed they are improving the replication process, you don't see much publicity on this. And but you might very well, if you're interested, to talk to him. If you do, give him my regards, because he had a great deal of difficulty when MIT itself was not supporting cold fusion. Why, by the way, would they be disposed against it? Not from just from scientific point of views. Is it competes with plasma fusion, hot fusion, which, as you know now, has become an even hotter subject with all sorts of claims going on. And what's the ultimate issue? Getting more energy out than you get in. In other words, if you look at the claims at Berkeley, at the Livermore Laboratory, with the method using laser fusion, when they said, we now have a sustained excess heat produced, energy produced, for, I don't know, a couple of minutes or something like that. They don't count the fact that of the energy that you have to put into the laser. Mm-hmm. To operate those super lasers requires a huge amount of energy. So, in any case, is even hot fusion, all of these startup companies, is any one of them going to work? There's a lot of investment going into them. I haven't studied all the differences. There are all sorts of different configurations. Will cold fusion ever develop into something people can use in their home? I don't think so.
What do you think? Yeah, do you think, like, let's say from my side, which is like more involved in nanoengineering of materials, so it seems like maybe there is a way, like introducing artificial cracks or defects, or like engineering, let's say, even starting from palladium.
Yeah, I think that's the area people could focus on, because chemical reactions occur differently at small cracks. And by the way, this is also true in the human body regarding the behavior of water in the human body. The interactions of water with molecules in the body can be viewed in the same spirit as what happens at cracks in materials. I had a very bright graduate student at MIT who completed a thesis on what cracking in material, defects in material is all about. And you really have to understand the nanoscopics of that. You really have to also be able to calculate, you have to go into the quantum chemistry of those materials. And Mark Eberhardt, this is the student who did this, even wrote a book on it called Why Things Break, which was, I think, modestly successful as a book, trying to explain what happens in materials, why they break. And this was all based on his thesis at MIT and in material science. And he ended up, I think he's at he's at the Colorado School of Mines, where he's continues to do this work. But to answer your question, you could devise a research program. If you're interested in low energy nuclear fraction, the low energy nuclear, you could establish a research area in that for that part of the problem, and trying to understand how cracks in a particular material like palladium. But I wouldn't be surprised if people are doing this at other institutions now. But the final word is, I don't think we're going to see cold fusion reactors in the home any day soon.
What based on your kind of varied career, like science, filmmaking, everything, what's your advice to like somebody that's just getting into it, like somebody in their early 20s? What's your, kind of if you had
Well,
to
my
give advice?
advice is, don't become a particle physicist. Don't go into that area. I think the whole future of CERN and discovery of new particles, I think if you're a theoretician working in the quantum area, learn as much about the real world of materials and chemistry. In other words, try to balance out your education in both chemistry and physics. And that's what's great about materials science, because I don't know what's happened to the material science department now at MIT, but what I'm saying is studying materials ranging from cold fusion materials to possible cosmical materials. That experiment I described that was done in Germany, I would love to see that done at MIT. Trying to duplicate in the laboratory at much less expense the interaction of radiation with stuff that simulates cosmic dust, and then look for these things coming out like they did in Germany. It's all about thinking more as a generalist. I think our education, maybe even at the graduate level, is too specialized. In other words, there's not enough breadth to it, because many of these unsolved problems can be approached from all points of view, and whether what I'm saying is true or not true, I know that the strange thing about this model, even when I published it, and even though it's been downloaded a lot, I've never had a criticism of it, a formal criticism from an astrophysics person. In other words, I would love to see people coming out and
That's
criticizing
how it
it,
goes.
in the literature saying, look, this stuff by Johnson is totally crazy. And why would we believe him anyway? And but I've had none. And I encourage people to do that.
Very cool. Yeah, that might be a fun project for a young scientist. That's a
Okay,
good
I
Okay.
one.
think we can talk about it maybe like in one more episode.
Another
But I think
time.
today
Yeah.
it was really great to, I mean, go
I'm
over
sorry I went over time,
one of
but
those
Oh,
big
it's okay.
physics mysteries. Yeah, yeah. Thank you, Keith. That was really insightful conversation. I'm fascinated by the stuff we discussed today.
During the recording of this podcast, Keith often changed the subject to his theory of the chemistry of dark matter. Since we could not verify whether the theory was legitimate or had gone through any significant peer review, we decided to move it to an appendix. If you'd like to hear it, stay on.
all right. So, where was I? So anyway, at this time in the 90s, all these things were happening at the same time, and the idea that these water clusters might have a relevance in the dark matter and dark energy areas, it was intriguing to me. And then I started looking in at that time in the late 90s. By the late 90s, they had discovered dark energy. In 1998, they were doing these measurements of the light coming from distant supernovae called 1A supernovae, and discovered these were, by the way, arduous experiments. Almost anything you do in astronomy or astrophysics on an observational level can take years, and your whole life career can be spent on one problem. And so in 1998, they discovered that by looking at these distant stars, the light from the distant stars, that the universe was not just expanding. That was, of course, as you know, a discovery in itself when Edward Hubble, early in the 20th century,
Was it at that
uh,
time by Hubble? Did he introduce the dark energy, which is
no,
responsible for the
Hubble,
accelerated
Hubble,
expansion?
see, up to Hubble, uh, most people believed the universe was static. Okay? In other words, you just, first of all, it took a long time to realize that these uh, distant objects you saw were galaxies, were huge groups of stars. Einstein himself um, was concerned about, in his general theory of relativity, he postulated something called the cosmological constant. He had to add a term to his equations of general relativity to keep the universe static. Okay? And then, interestingly enough, he disbelieved it and threw it out. He said that was one of the worst mistakes he ever made. But anyway, the idea that there was something called a cosmological constant that kept the universe static, was present pretty much, and for a long time, and still until very recently. And things have changed, and I'll get to that in a minute. And this is stuff that's happened only in the last couple of weeks, believe it or not. In 1998, they discovered the universe is not just expanding, as Hubble had discovered observationally, um, it was accelerating in its expansion. Okay? So some kind of anti-gravity is pushing the universe apart faster than Hubble's original idea, and and they did these observations over and over again, and it was right. And this is where dark energy was born. So dark energy was not born with Hubble, but with these three guys who co-won the Nobel Prize in physics for this discovery. And so ever since 1998, we've had this idea that, well, what is pushing the universe to accelerate? It's got to be some kind of energy. and this is called dark energy. Now, still, most people believe, most physicists, the establishment, people who are experts in this subject, believe that there are different problems. In other words, dark matter is one problem. Let's try to find out what it is. And dark energy is another problem. Let's try to find out what it is. And there are hundreds, if not thousands, of theoretical astrophysicists who try to explain these phenomena separately. At the same time, for almost 50 years, dark matter, which is a much older subject, what is dark matter? It's an invisible substance that accounts for 30% of what's postulated to be 30% of the universe, which is some invisible substance. In other words, it doesn't emit or absorb light. It only interacts gravitationally with other stuff in the universe. And for 50 years, people have been designing and executing experiments to try to identify particles, elementary particles, that have been postulated to be this dark matter. Now, this is a whole other issue in physics, because the people who work on the theory side, are what we call elementary particle physicists. What are elementary particles versus non-elementary particles? Elementary particles are the electrons, the protons, the mesons, etc., etc.
No
The last
chemists
one I just,
involved.
pardon.
No chemists involved who would study molecules.
Exactly. No chemists involved, and so on. And the training, of course, you got to remember also that the training of particle physicists is very different from the training of chemists and material scientists. But I'll say at the outset, there is a material science of the universe. There's a material science aspect of what I believe is actually going on, which none of the experts have looked at. And cutting to the chase, I believe it involves water. I may be totally wrong about this, but anyway, the thing is that I'll give my reasons for this. There's a principle called Occam's razor. You've heard of it. It's a principle that if you're trying to explain something that has many other explanations, many of which are very complicated, the simplest explanation is usually the one that works out. It's called Occam's razor. And there's also an aspect of science which I believe is about beauty in science. John Wheeler, my freshman physics professor, said many times to the class that once you understand what's going on in the universe, it'll be so simple, and you'll wonder why it hasn't been found before. Okay? And I believe this. I think that Occam's razor, simplicity, and beauty have a lot to do with almost any area of science. And cosmology. Now, what do we mean by cosmology? Cosmology has become kind of publicly the queen or king of the sciences now, because practically everything you hear from the press has to do with the discovery of the latest results of the Webb telescope, the newest space telescope that we have, and earlier on the Hubble telescope. In other words, it's become a public thing. A lot of it also has to do with people's interested in UFOs, and is there life in the rest of the universe? Are there technological civilizations in the universe? One of your last interviews was with Avi Loeb, who believes very much in this and tries to find the remnants of extraterrestrial technology and so on. And so the whole public PR in science has a lot to do with cosmology, what's happening in the universe. Why is this? Again, I think it has a lot to do with UFOs and so on. But the thing is that um, getting back to the role of um, material science of space, what's out there? I mean, if you take a basic astronomy course, you will learn that, well, stars were born basically from hydrogen, and which was transformed by fusion again into helium and to lithium early on, and uh, and then the heavier elements like oxygen and finally iron and heavier elements were formed much later. Now, as far as beauty in science is concerned, and the questions of what's really going on, Carl Sagan, I don't know, you guys are young enough probably to maybe have not experienced Carl Sagan's television broadcasts of the 70s and so on. But Carl Sagan was an astrophysicist initially from Harvard, and then he went to Cornell, talking about the connection of what was happening in the universe to what's happening in the history of the world and so on. But one of the things he always pointed out, he says, we humans are made from cosmic dust. It turns out that the universe, galaxies in the universe, have a lot of dust in them, and cosmic dust. And it's a major part of the materials constituency of galaxies. Now, where does this cosmic dust come from? And some of it's very nanoscopic. So not only microscopic but nanoscopic. How was it created? Well, it turns out if you look at even the most recent work in astrophysics and observational astronomy, you will find that cosmic dust is the remnant of supernovae explosions. And in other words, when a star collapses from its normal state in its lifetime, it reaches a point where it's run out of the nuclear fuel and it collapses on itself gravitationally and explodes. Now, there are different types of these supernovae, but more and more of them are being discovered. And particularly in recent months, the Hubble telescope, not the Hubble telescope, the Webb telescope, which I think you must have heard about also in the news, has been making absolutely astounding new discoveries, some of which are questioning now the standard models of cosmology. Okay? But they are adding to the mystery of dark matter and dark energy. What's happened just literally in the last month or so, there have been two major discoveries reported in the news and published. Number one is there's far more water created shortly after the Big Bang, the origin of the universe, than was ever believed before. One of the criticisms of any model that brings water into the picture of the cosmos has been, well, is there enough of it? Because the standard cosmology believes that 30% of the universe is dark matter. There's not enough water to explain all of that dark matter. And secondly, as far as dark energy concerned, what does water have to do with dark energy? That's 70% of the energy of the universe. And of course, that leaves only a few percent for real materials in the universe, the stuff we can see glowing, in galaxies and so on. So anyway,
Keith, actually, when you say what we're seeing, so I understand that we can collect like different types of signals, like let's say electromagnetic of different part of the spectrum. So obviously, like it has been done in the visible range, in like radio frequencies, but then those nanoclusters, they supposed to emit some signals. Is it that we're not collecting this signal properly, or what is your take on that?
okay, I'll get to that. First of all, what do we see? We've gotten to the point in astronomy where we can sample the whole spectrum. The Hubble telescope looked at the visible part of what you can see. The um, Webb telescope is looking at the infrared. Okay? Now, the thing that's interesting about water at this nanoscopic level, these water clusters, is that the part at which they interact is in the terahertz region. So this is a challenge. The terahertz part of the electromagnetic spectrum is between the radio region and the far infrared. It's a very narrow region of the spectrum. And terahertz spectroscopy itself has become a specialized field. For example, you can use it to detect at an airport. You can use it to detect explosives and so on. And it has the property that it will penetrate the body without doing it any harm, which you can't say is true of X-rays and other radiation. So, as far as astronomy is concerned, you have visible astronomy done by bigger and bigger telescopes on planet Earth, and then you have the Webb telescope, and you still have the Hubble telescope, specializing in infrared and visible region of the electromagnetic spectrum. However, these water clusters, their vibrations that I talked about, actually occur in the terahertz region. So they're far from the far infrared region, and they're not in the visible region. A terahertz region, again, is between radio frequencies and infrared. So the thing is that it's very hard to see these spectroscopically. And also, their terahertz spectrum, what you can measure in the terahertz spectrum, and there is work done in that region, uh, is very dense. In other words, there are specific spectroscopic signs of this particular unit that are distinguishable in principle from other water arrangements, but it's a challenge to see these directly. However, the good news is that there have been experiments done. When I first was writing this paper that I published in the International Journal of Astrobiology, just at the time I was writing for that paper, there were some experiments done at the Max Planck Institute in Germany where they tried to simulate cosmic dust. And what happens to cosmic dust when you bombard it with cosmic rays? Cosmic rays, of course, are high energy rays that come from other things in the universe. And so what they did was they simulated cosmic dust in the laboratory in a vacuum that compares to that in space, and they bombarded it. And then they found spectroscopically, they were able to use mass spectroscopic that the simplest cluster that came out of their experiments were ejected from the cosmic dust were these water clusters, basically. So there is published experimental evidence that these water clusters, when bombarded, on cosmic dust are ejected, but they're not ejected from just the cosmic dust. The cosmic dust is covered by a form of water, which is amorphous water. Now, amorphous ice, water ice. This, as you probably know, there are many different structures of ice, water ice, that we can examine in our refrigerators and so on, that you can create at various pressures and temperatures. But amorphous ice is very unusual to create on in a laboratory. In other words, so what they ended up doing was very challenging. They were able to create amorphous ice on this simulated cosmic dust and then bombard it and observe that these very clusters were ejected. And that was good news to me because I was speculating that these clusters would be ejected from cosmic dust from cosmic ray bombardment. So we have that experiment done in the laboratory. And so that's a way of identifying the possible presence of these things in space from an experiment done in the laboratory. Where does this cosmic dust come from? It comes from the remnants of supernovae explosions. Again, that's a thing that Carl Sagan was talking about 20 some years ago. More, I think, actually, and even had a television program about it. Now, as far as astronomers are concerned, cosmic dust is an annoyance. In other words, it's something that obscures your looking at what you want to see. In other words, if you're trying to look at a star, the possibility that there's a solar system around a star, there's a planet. If dust is in the way, it's in the way. And so cosmic dust has been looking to most astronomers as a negative thing. But in fact, from the point of view, especially from my own personal point of view, it's an important factor, not just in the dark energy problem, but also in the origin of life. And I'll try to explain that connection in a minute. Is this making sense, by the way?
Yeah. So Keith, essentially, did I correctly understand that that ongoing experiments on, let's say, dark matter, they were looking for wrong things, and it turned out to be just dust particles in the universe? And maybe if you can comment about how are the calculations done to predict that there is a dark matter? Did astronomers only take into account the star's mass, like the mass of all the objects, like let's say I don't know, like black holes, stars, like all this big and massive stuff, and then the dust was just missed in this equation?
Okay. Again, most of the people who try to explain dark matter from a theoretical point of view are particle physicists. They are not material scientists. They're not chemists. They're trained in a very specific, highly mathematical discipline. And over the years, at least 30 years, if not more, they've come up with theoretical models, purely mathematical models, that there exist elementary particles that have not been discovered yet in the so-called standard model of elementary particles. And the most popular ones have been the WIMP, weakly interacting massive particle, and then something called the axion, which is totally different and totally different particle, and named after once popular soap, dishwashing soap or whatever. The thing is that then over the last 30 years, if not more, they've tried to detect these particles with elaborate experiments that go underground, deep underground, for example, in former mine shafts and ones that they dig fresh. There are even some still being dug, as I understand, in certain places in the world, but there are dozens of these places now. And the detectors consist usually of a liquid that, if one of these postulated particles comes in, they'll be able to measure it, detect it with the right detection equipment. And these places are huge. The people who work on these experiments for years, many of them are famous professors in departments of astrophysics, and they send their graduate students and their postdocs deep down in these shafts, and with miners' hats on. It's like being.
Is
It's
there
like being.
such a shaft nearby Massachusetts? So I would
I
love to
don't
visit
think.
that.
I don't think there's one in Massachusetts. No, but they are scattered all over the country and other countries, especially Australia being one of the last. Anyway, so the thing is, um, they've been looking for these things, and what's happened with the WIMP is that was very popular up to about 3 or 4 years ago. And now, even though there's still some experiments going on, the community of specialists believes they don't exist. And there's another reason for them not to exist is there's a theory of particle physics called supersymmetry theory, in which you take, until the discovery of the Higgs boson in 2012, I think, at CERN, the famous, uh, powerful elementary particle uh, experimental place in Switzerland and so on. Until that discovery, there was a so-called standard model of elementary particles, which over the years they had established one by one until all of the elementary particles, except for the Higgs boson, which, by the way, no one believed in existed. Higgs himself proposed it many, many years before it was discovered. But CERN, in a sense, was, how can I say it, the Large Hadron Collider part of, was built to try to find the Higgs boson, because it was believed that that would be the final list of elementary particles that would satisfy the standard model, what is called the standard model. However, there's another theory, again, called again, purely mathematically derived, which is called supersymmetry, which advocates there exists a whole bunch of other elementary particles that correspond one by one to the standard ones. And it was thought that as soon as the Large Hadron Collider at CERN was functioning, they would discover these supersymmetric particles, and one of them would be the the WIMP. In other words, it turned out the original mathematical WIMP physics was consistent with what they believed they could achieve at CERN, but they found none of them. And in fact, really nothing new has been found at CERN since the Higgs boson in 2012. And this is very disappointing, considering the size, the magnitude, the thousands of people who work there. Again, thousands of graduates, postdocs in particular, work there to try to make new discoveries new elementary particle discoveries. But there have been none since the Higgs boson. Now they want to build a bigger one because they believe, oh, well, this is just an energy problem. We need higher energies. We have got to smash protons and electrons together at much higher energies to see anything new. And there's, of course, a lot of opposition to this because of the cost. But anyway, the thing is that the Higgs boson, the WIMP, was invented from pure mathematics. The same is true for the axion. And there have been experiments, and they're now focusing on axions with some of the same types of experimental installations. There's even been one at MIT. I don't know if it's still operating, called Abracadabra. It's not a big piece of apparatus, but it's been functioning. But the last time I looked, it hadn't found anything. So thus far, there's no experimental evidence for axions. Yes, I think you asked the question, what about black holes? What about, well, there's one proposal that mini black holes or even microscopic black holes might exist, and that might be dark matter. And then there's what is called they're neutrinos, a particular form of neutrino that has been a candidate for dark matter, but they haven't found those either. So essentially, is there anything left? Well, not really. Those are all of the possibilities. There are more exaggerated theories involving multi-dimensions. And for example, you've probably heard of something called string theory. Well, string theory has been out there now for a long time and has gone through several evolutions. And even today, I received a copy of New Scientist magazine where somebody is proposing that, well, if you simplify string theory, then maybe our universe and dark energy can be explained by something called branes, BRANES, that our universe as we live in it is a brane in a higher dimensional. So there are all sorts of theories out there, highly mathematical theories, by very intelligent people, none of which have any experimental or observational validation. Tens of thousands of publications on this whole area of physics. So let's see, where are we? So my own interest in this subject was stimulated by a combination of things. The working on water clusters from a very practical goal, the point of trying to clean up diesel fuel, to their possible role in biology. The human body is 70% water, the brain is 90% water, and much of that water is nanoscopic. In other words, when you try to, and this is, by the way, this has been validated by observational results. For example, one of the first observations was in certain types of tissues, you can actually see X-ray evidence for these pentagonal arrangements of water molecules. In other words, indications of this shape, again, in the human body. And
what would be like the if you could had unlimited funding and you could fund one experiment or like one set of experiments on this topic, what would it be?
on the dark energy and dark matter problem, yes,
or just
well,
this
as far
structured
as,
the structured water question, or I don't know how you would call it, but
well, first of all, regarding the subject we're talking about, dark matter and dark energy, what I would do is I would use the Webb telescope, this new telescope, to do very accurate measurements of the water, that water vapor they're now already seeing. That's the experiment I would do with NASA. And I have actually communicated with a few people that I'm in contact with at NASA to try to get to an experiment of this type. You will be able to detect their presence in space spectroscopically in the terahertz region. You really have to look at the terahertz part of it. And I'm not sure that's possible with the Webb telescope or sub-adjunct to it, but that would be the goal, to identify, because you can identify very specifically what the spectra of these water clusters
Is it
are.
possible to reproduce it here on Earth first and like know the spectrum before looking in space?
Yes, and those are the experiments that I mentioned. Uh,
Hmm.
the experiment that I talked about in Germany, Max Planck Institute, where they
Mm-hmm.
bombarded cosmic dust with radiation, which then ejected these water clusters, and they measured the water clusters so they know exactly what they are.
Hmm.
And so how can I say, that would be the experiment I would do in space. However, that said, two things have happened just in the last month or 2 months. Trying to remember, time goes fast. One is there's been some recent research done by a man named Whelan, Wehlan, uh, in Europe, uh, using the results of the Webb telescope. They have found evidence for water being created much earlier after the Big Bang than was ever suspected. So one of the criticisms you can make about this whole idea of water being relevant to dark matter or dark energy is its very existence over the whole history of the universe. The standard, the standard thing you learn or have learned, textbooks in astronomy, is that oxygen was not created early enough in star formation to create water. You have to have oxygen to create water. There's this general idea that heavier elements were not created, but just in the last month and a half, there's been this Nature Astronomy, prestigious journal, Nature Astronomy paper published by this group concluding that water was present to the same degree that it's present in our solar system, okay, as early as 100 million years after the Big Bang. That is really early. In other words, it was believed at that time you were in something called the reionization period, where things didn't happen. Stars were not created. And there's these special stars that were formed very early. They no longer exist, called um, population Roman numeral 3 stars. They were huge. They were up to hundreds of times the size of our sun. Very unstable. They exploded very quickly. They had very short lifetimes. And they would explode, and they would create all the stuff I'm talking about in my model, the cosmic dust, because that's what's left over. And all the materials, they created the heavier elements. So oxygen was created and was able to combine with the hydrogen to form water. So that's the one discovery that's happened in the last month to 2 months. And then number two, by a totally different group that has been working now, I think, for 5 years on mapping out all of the galaxies that they can see with a certain telescope called the Dark Energy Spectroscopic Instrument, located at Kitt Peak in Arizona. And this has been done over 4 years. And they've looked at the light emitted from all of these galaxies. How many galaxies? Around 15 to 17 million galaxies. Okay, that's a lot to do with one telescope. And they studied their motions over this period of time and come out with a conclusion that contradicts this principle of cosmology that has been around for all time, called the cosmological constant. It's the idea that this dark energy that we're talking about that is accelerating the universe is a constant. And it was the thing that was originally invented by Einstein, but then he threw it away. And then in 1998, they discovered dark energy and they had to bring it back. And one of the things about that cosmological constant is that it's not really a constant, and that's what these new discoveries have found, is that the dark energy is not increasing, it's decreasing. In other words, if you go back to the Big Bang and you take their measurements, and by the way, this is a huge amount of work. The paper they've just put on as a preprint has, I don't know, 200 or 300 authors on it. So this is not done by one person. It's done, and that's, by the way, true of most stuff that's done in astronomy these days. Multi-authored papers. It's hard to find a paper with one or two authors on it anymore in almost any subject. And so the thing is, they found that the claim is that to the accuracy they're able to claim, dark energy is not a constant. It's not a cosmological constant. And if you go back to the big origin again, near the Big Bang, and trace it down to the present, it's decreasing from an earlier value, which is not predicted by standard astrophysical theory. And they call this phantom energy now. They're using this terminology. And if you carry this through to the future, distant future, what does this imply? Well, it implies that the universe will not run out. The standard theory of cosmology based on inflation theory, invented, by the way, by a guy at MIT named Alan Guth in the physics department. You probably heard of him. Inflation theory. The idea of inflation theory is that the Big Bang occurred very, very fast, and then the universe and dark energy will fizzle out, and the universe will end in nothing, called the Big Rip, basically. Because the dark energy will be assumed to increase rather than decrease. In other words, dark energy is getting stronger according to standard theory and will overcome matter and gravitational attraction, and the universe will end. And it's called the Big Rip. That's been the standard model of cosmology. But these new results from DESI, D-E-S-I, show quite the opposite. That the universe, the dark energy, is actually decreasing. Now, it turns out that when I wrote my paper that was published in 2021, I come out with an equation for dark energy based on, I'll explain that a little bit more eventually, but the thing is that my results suggest that dark energy will decrease with time. So I was happy to see these results because it's a much more positive result philosophically, because it allows you to postulate that the universe will not end, dark energy will run out, the gravitational attraction by all the remaining matter will take over again, the universe will then contract, and then go back to something like what happens at a Big Bang, but it may not be an explosive Big Bang, and then it'll re-expand. The same thing will happen again. This is called a cyclic model, which is quite opposite to the inflationary models. There's another problem with inflationary models, which you've probably heard about, called the multiverse, which my model and other cyclic models refute. In other words, there's no such thing as a multi-universe in reality. We live in one universe. It's going to expand, and then it will contract, and then it'll expand again. And what's the length of a cycle? Well, it's around a trillion years. So we don't have to worry about it. But the thing is, the existence of the universe being cyclic, and I should point out that there are at least two prominent theories of cyclic universe. One by Paul Steinhardt from Princeton, who with his students have been arguing mathematically for a cyclic universe, and then Roger Penrose, Nobel Prize-winning physicist from England, who has his own cyclic universe theory. And there may be other ones, I don't know, but mine is very simple. It's based on the properties of water. I know this sounds far-fetched, but what happens is, in my model, as you create more of these water clusters from cosmic dust, remember, there's a cyclic aspect even to that. You have stars, they explode, they leave dust, the dust collects water, amorphous water on its surface, which is then bombarded with cosmic rays, and then ejects the water clusters. Now, these water clusters then have a spectrum, electromagnetic spectrum, that qualifies them as dark matter. In other words, you cannot see them. They do not broadcast light. They transmit light through them, because all their activity occurs in this terahertz region, which is this very narrow region of the electromagnetic spectrum. And secondly, unlike the standard model of dark matter and dark energy, which are viewed as separate subjects, they are actually connected as dark matter to dark energy, because from their very form, they constitute Casimir cages. Have you guys heard about the Casimir effect?
Yes, yes. It's like the pulling force between the two planes due to the vacuum.
And that's been demonstrated in the laboratory. And it's explained by understanding how the vacuum energy, in other words, empty space, the vacuum, with nothing in it, according to quantum theory, is a very active thing due to the uncertainty principle of Heisenberg. In other words, it's a kind of at the deep quantum level, called the Planck level, it's constantly transforming itself, and it has a certain energy associated with it. Now, if you try to calculate that energy by the best method known to theoretical physicists, called quantum electrodynamics, you get a number for the vacuum energy that's 120 orders of magnitude too large. And people, from a practical level, for years have been trying to understand, can I extract this energy? It's huge. However, the answer you get is wrong, because this huge energy that you calculate is nowhere near the actual dark matter energy, which they can actually do measurements, observations about, and come out with a number. And it turns out that the dark energy density, in other words, if you look at dark energy per unit volume, like per cubic meter, it's a very small number, nowhere near the 120 orders of magnitude that you calculate. So most physicists who know about this say this is the worst mistake particle physics has ever made. come out with this number. But what I've found and speculate about is that these water clusters, once you create them, eject them from the cosmic dust that Carl Sagan talked about, even though they're in density, they're very, very low density. So I don't want to compare them with the amount of hydrogen atoms that you find in space. But nevertheless, they have a property called Rydberg matter property. And again, this is a result of elementary understanding about atoms. It turns out that many atoms, including hydrogen, have high energy states that you can identify optically called Rydberg states, named after a guy from history who studied the first spectrum of hydrogens. Well, it turns out these things also have Rydberg states, high energy states that are very diffuse, that surround them. You can calculate these from quantum mechanics, from quantum chemistry. Now, so if you have one of these buckyball or pentagonal dodecahedral clusters in space here, and you have another one far away, which is likely to be because they're not very dense, they can still interact through two things. These Rydberg states can overlap even over long distances, and then you can have something called quantum entanglement, which is, again, a very popular topic now in physics because it's been demonstrated to be real, that objects at the quantum level, very far apart, even in space, galaxies, for example, actually, if you do an experiment, if you do an observation on a pair of these objects, you'll find that the other object in the pair interacts or is affected by the observation on the first object. And Einstein called this spooky action at a distance. Spooky action at a distance. And at the time when he didn't believe in it, even though he wrote a paper or two with co-writers on trying to explain it, it's been observed. And it's been observed in cosmology. So what happens, I believe, then, is that these water clusters, once they're ejected from cosmic dust, even at very low density, can effectively collectively interact with each other to form this something called Rydberg matter. Now, I didn't invent the idea of Rydberg matter. It's been invented by other people. And it has been verified in other substances experimentally in the laboratory, as far as I know. But in any case, once you have that, you can then have a reasonable argument that these things are they're not elementary particles, but they are nanoparticles that are a form of dark matter. Now, this does not rule out other forms of dark matter. If somebody comes along tomorrow and says, oh, we finally found a WIMP, or we finally found an axion, fine. But what these shapes have is they are Casimir cages. So this brings me back to the Casimir effect. The Casimir effect, as you correctly described it, is an attraction of two plates. Now, this can be done in the laboratory. So we're talking about macroscopic objects that will be attracted to each other because the vacuum energy outside the plates puts a pressure on these plates and brings them together. And the Casimir effect has been discussed. I mean, there are other explanations for it, but this is the explanation based on the vacuum energy. So what I calculated, found is that these things are microscopic or nanoscopic Casimir. Each one of these pentagons here, opposing ones, are like the plates you're talking about with the ordinary Casimir effect. And there are many of them. There are of course 12 of these opposite. I mean, there's six opposites, and they attract each other. Why? What are they doing then when they attract each other? They're absorbing or they're capturing. I'd rather use the term capture. They're capturing the high energy photons. Those are the light particles. They're virtual particles, which are associated with the vacuum. In other words, if you look at the vacuum, they're basically creating virtual particles. If you stick to the electromagnetic picture of them, virtual photons. Photons are the particle equivalent of electromagnetic interactions. So the vacuum is full of these virtual photons. So when you calculate it by quantum electrodynamics, you get the right answer when you do the calculation. But it's 120 orders of, when I'm saying the right answer from the computational point of view, but it's not the right answer that you measure. This is called the vacuum catastrophe. And it's been like a major problem in theoretical physics, and also underlies the whole dark energy thing, because it leads to a much larger dark energy density than you measure. So what's happening, I believe, is that these pentagonal dodecahedral water clusters are acting as cages, Casimir cages, which then capture that excess energy that you want to get rid of. And you're then left with a much smaller amount of energy.
I was going to ask you, is it the only type of cluster? So there are many different forms and shapes and configurations.
Yes, there are. And in other words, you can build larger ones, okay? You can form larger ones, which are like combinations of these. And there are even ones that are in the shape of an icosahedron, which is a higher, but it's the same symmetry, but it's higher, it's a different arrangement. So that's the symmetry of buckyballs. So in any case, then you end up being able to have an argument for dark energy, which connects dark matter to dark energy. The dark matter, this form of dark matter, is capturing the excessive dark energy that you measure, that you calculate, and you're left then only with a small amount. And this all occurs at a very specific frequency, 1.7 terahertz. The vibrations that occur at 1.7 terahertz. And again, we don't have time. I don't want to take up all this more of your time. But the thing is, it's the same frequency at which molecules interact with water in the human body. Now, this sounds far-fetched, but this is the connection to astrobiology and the origin of life. There's a whole theory. One of the many theories for the origin of life, and there are many of them, is the RNA world, ribonucleic acid. Now, RNA is
Guys,
a
I
helical.
think we can't we won't be able to cover it in this episode just because it's already 2.5 hours long. So if we go into the
Yeah, I'm
origin of
sorry.
life thing, I think it's all good, but it's
More.
just we just have to do it another time.
Well, anyway, there's a connection, and there's a fundamental frequency common to both the subject of this discussion and astrobiology, and it's a specific frequency that you can actually calculate and measure, and it's about 1.7 terahertz.
So I guess the fundamental prediction is that once we have terahertz telescopes, we can basically see what's out there. If this
I believe so, but I think there's a lot of
is out there.
inference, especially now since water has been discovered so early on. And that's where the Webb telescope is looking, so early on in the history of the universe. There'll be people doing this. And I think you'll be able to infer much of the information eventually by doing this type of experiments. Whether you can do it directly with terahertz spectroscopy or some variant of it, I don't know yet. But I was hoping that my publications would stimulate somebody. But now you don't. With the funding situation going on in science right now, it doesn't look too promising.